Hello everyone, my name is Saeed Nejati and this is the introductory talk for our paper on machine learning based splitting heuristic for divide and conquer solvers. Divide and conquer SAT solvers accept a Boolean formula phi as an input and split it into several different smaller subformulas and solve the subformulas in parallel using sequential SAT solvers. And the way the splitting works in this scenario is that the solver picks a variable, for example, x, and set it both to true and false, and derives the two subformulas out of that, and then it could further split the resultant formulas into smaller subformulas. And the process of picking these variables to split the formula is called the splitting heuristic. And the general goal of splitting heuristic is to minimize the runtime, of course. But to be able to achieve the minimizing runtime goal of the splitting heuristic, we need to be able to answer this question of how to measure the quality of a splitting variable. So generally, people quantify this using a performance metric function that from a formula phi and a variable within that formula, we assign a real value to each variable. And then the splitting heuristic process becomes picking a variable that minimizes its performance metric. In our work, we define the performance metric to directly be the runtime of splitting the formula phi over a variable v once and solving the resultant subformulas in parallel. But the problem with this formulation is that we need to know the runtime of solving phi and v and phi and negation of v. And in general, predicting the runtime of a solver over any general formula is a very challenging task. But the observation we could make here is that we don't need to know the exact value of the PMs, and we only need to be able to compare the PM values for all of the variables to be able to compare them. So in other words, we don't need to know the 0.98 for V2. We only need to know that PM value of V2 is larger than V1. And we define this pairwise function that given a formula and two variables within that, it compares the PM values of Vi and Vj and gives us a value of 0, 1 based on that. And because it's a 0, 1 output, we could train a binary classifier to approximate this pairwise function. And learning this pairwise function, we could use it as a comparator to find a minimum element in the list of variables that are candidates for splitting. We implemented this system in painless parallel SAT solver framework and compared it with the baseline and state-of-the-art triangling on benchmarks like SAT competition benchmarking cryptographic. And on 16 cores, we could see that we outperformed both state-of-the-art and baseline painless. Thank you very much. Hello everyone, my name is Saeed Nejati, and in this presentation I will talk about our paper on machine learning based splitting heuristic for divide and conquer SAT solvers. This was a joint work with Ludovic Frioux and Vijay Ganesh. So parallel SAT solvers have two dominant architectures. One is portfolio solvers and the other one that we focus on is the divide and conquer solvers. In divide and conquer solvers, the solver splits the formula into several subformulas and solves them in parallel. The backend solvers and sequential solvers could share information with each other in the form of flared clauses. The process of splitting the formula is as follows. The solver picks a variable x within the formula phi and generates two subformulas phi1 and phi2 by setting x to false in one of the subformulas and setting x to true in the other one. And it could repeat the same process for phi1 and phi2. The general formula phi is SAT if at least one of these backend solvers returns SAT and say that one of the subformulas is SAT. But for to prove that the whole problem is unsat, we need to prove that all of the subproblems are unsat. So this is a schematic of how this splitting of the search space and the formula happens. For example, you could see at the top, if we pick variable x2 and set it to both true and false, we generate two subformulas, and on those subformulas we could, for example, on the left side pick x5 and split the problem further down. We might get some unsat on even on the splitting of the formula, but if we do the splitting, we might get, for example, this phi1, phi2, and phi3, which are just the constraint versions of the original phi problem with the path from the root to the leaf of that subformula itself. And then all of these subformulas of VI's will be given to sequential SAT solvers to be solved in parallel. The process of picking these variables, which variable to pick at each of the branches, is called the splitting heuristic. And the top question that this splitting heuristic is going to answer is that how to divide the search space so the conquer part becomes easier. Now, one might ask that how do we know that a splitting variable is good? In other words, if you want to generate or create a splitting heuristic, you need to know how good the variable is in order to say which one is the best variable for splitting a formula. So we need to quantify the quality of these splitting variables, and the common way and definition for this task is through a performance metric function, which accepts a formula and a variable within that formula and assigns a real value to a variable. So in terms of the performance metric, the splitting heuristic is just looking for a variable that minimizes the performance metric. The ultimate goal of, similar to any search heuristic, of the splitting heuristic is to minimize the runtime. But we know that from the literature that predicting the runtime of an algorithm on an input is a very challenging task, especially in the case of SAT solving. And what researchers do is that usually they generate some handcrafted heuristics and compute some metrics that are proxy for runtime. So they minimize the proxy metric instead of minimizing the runtime, in the hope that minimizing that proxy heavily correlates with, strongly correlates with minimizing the runtime. So for example, in some works, the performance metric is just activity of the variables and that are generated through the branching, for example, V6 or LRB. In other cases, the performance metric is defined by how much a variable generates propagation when it is assigned. And for example, in the look ahead and cube and conquer type solvers, when you set the variable to true and false, the difference with the original formula is calculated using some heuristic, and those heuristics for left and right branches will be mixed into one number. And in all of these methods in the literature, there are some scores being assigned to each of the variables, and then we look at the scores and pick the variable with, for example, minimum score or maximum score. And you could see that this as a ranking of the variable in a form of pointwise ranking. In a pointwise ranking, each item in a list to be ranked is assigned a score, and the list is sorted according to that score. So all of these methods are some sort of ranking assignment to variables using a pointwise ranking. In this work, we define the performance metric to be the runtime itself of solving a formula when split once over a particular variable v, and then solving those subformulas of splitting the formula over the variable v in parallel. But the problem with defining the PM in this kind of way is that we need to know the runtime and status of subformulas a priori. But we could actually build a machine learning model that trains from the features of the formula and variables to a predicted runtime. But as we said in previous slides, predicting runtime in the case of SAT is a very challenging task. So what do we do now? One observation that we made in this work was we're actually looking for a minimum element in a list of elements ordered by PM. So instead of predicting the PM values for each of the items in the list themselves, which is a hard task, we only need to predict how they compare to each other. So for each variable, we don't need to exactly know what the actual score should be, what the runtime should be. The number of that runtime doesn't matter, because we only need to know if this variable performs a better splitting than the other one. If we train such a predictor, this predictor can be used as a comparator to find a minimum element in the list of candidates. And this forms a sort of pairwise ranking instead of a pointwise ranking. So the goal is that to formalize it, we could say, given two variables v and u in a formula phi, the question we're going to ask and answer is that, is v better than u for splitting phi? And we formalize this using this pairwise function, which accepts a formula phi and two variables vi and vj within that formula. And if the performance metric of vi is less than the performance metric of vj, it returns 1 and 0 otherwise. And because it's a 0-1 function, we could train a binary classifier to approximate this target function. So to train this function, we generate some data points, which are features of the formula and variables labeled with the comparison of the performance metric of two variables. So we form formula features of the formula phi, variable features of the first variable, and variable features of the second variable, and label it by the comparison of the performance metrics. So for formula features, we use features such as number of variables within the formula, number of clauses, average variable node degree, which means that how many, what is the average number of appearance of a variable in different clauses. For variable features, we use both structural features and search features. For example, structural features are such as how many times a variable appears in binary clauses, how many times a variable appears in ternary clauses, and so on. Search features such as propagation rate, for example, if you set a variable v to a certain value, how many other variables are set through propagation. Or for example, combined activities, branching activities, if you set the variable to true or false and combine it together, and so on. But because the number of features that you could come up with from a formula and a list of variables is a huge set of features, we need to do some sort of feature selection process. And what we did was that we did two passes on the list of features. One was addition pass, where we initially trained a model on this initial set of features and sorted them by the importance that was extracted from the, for example, in this case, random forest model, and sorted them by the importance and add them greedily by the sorted by importance. as long as they were reducing the cross-validation error. And we also did a deletion pass, because when we learn such a model and we want to employ it in a parallel SAT solver, in the runtime we need to compute the features on the fly and pass it to the machine learning model. So the computation time of the features is a great source of overhead for increased runtime of the parallel SAT solver. So it's important to take into account features that are easy to compute rather than heavy to compute. So we sorted the features by computation time, and we removed the very heavy features with the condition that they don't drop the accuracy too much. So we used random forests for training such a model, and we got an accuracy of 80% on a subset of instances from SAT 2016 and SAT 2017 SAT competition benchmarks. So for the experimental results, the framework that we implemented our heuristic in was the painless divide and conquer parallel SAT solving framework. We formed the baseline as the painless divide and conquer itself, with the flip splitting heuristic, which is the default splitting heuristic, and we tried to do an apple-to-apple comparison with painless in the case that we only replaced the splitting heuristic and didn't touch the other heuristics of the solver. And we also compared with other top divide and conquer solvers, namely Tringling, on two specific benchmarks, which were cryptographic benchmarks, which were encoding SHA-1 preimage attacks, and also main track of SAT competition from years 2018 and 19. So this is the cactus plot of running our experiments on cryptographic benchmark. A cactus plot should be read as each data point shows how many instances are solved in what time limit. So if you're toward right, you're solving more instances, and if you're toward bottom, you're solving instances faster. And you could see that painless itself was already ahead of Tringling in this case, but we managed to improve painless baseline by adding this new splitting heuristic and solving much more instances. And the case for this cryptographic benchmarks is that the hardness of these benchmarks is in a way that if you're adding and solving one more instance, it's a big step forward. And this is the experimental results for SAT 2018 and 19 main track benchmarks with 8 cores. So you could see that we significantly outperformed the baseline painless, and we are on par with the state-of-the-art Tringling solver in this case. But in many cases, we're much faster. And the interesting thing is that when we increase the number of cores, we see a big improvement in our case, which shows that our parallel SAT solver scales better with increasing number of cores. Here we solve more instances and much faster than Tringling using the same benchmark of SAT competition 2018 and 19. So to summarize, we proposed an machine learning based splitting heuristic that is trained from formula and variable features to ranking of the variables, and then picking the best variable as the variable that is going to be returned by splitting heuristic. So we took the approach of learning from data instead of creating another handcrafted heuristic, because the SAT solvers are considered a data-rich environment because they generate lots of statistics when they're doing the search and gather lots of information about the problem itself. So we could also say that we looked at the problem a bit differently. Previously, all of the splitting heuristics were proposing scoring heuristics to derive some scores for variables to rank them in a different way. But we looked at the problem differently and generated a new ranking method, which in the literature is known as a pairwise ranking method. And for evaluation, we evaluated our work on two cryptographic and SAT competition benchmark. We outperformed baseline in all of the benchmarks. And we showed that we're scaling better than the state-of-the-art Tringling divide and conquer solver when we're increasing the number of cores. Thank you very much.